Hello everybody, welcome to this 5th week of lectures on linear systems theory. So this week will be a little shorter module, but we will focus on some nice qualitative behavior of systems, and these are essentially to do with equilibrium points of the system. So, well, we would have encountered these definitions sometime during our previous courses, but we will give it a general setting here of the kind of systems that we will be dealing with. So, if I consider a differential equation of the form, so this could be non-linear, and also I put the t in just to also take into account the time varying nature of it. So, as usual x is an n dimensional vector, f is a vector field from R cross Rn to Rn with some initial conditions. Okay, so the basic definition of an equilibrium points is the following, that x star is an equilibrium point of this system 1 if it satisfies this equation. Right. So, f x star comma t equal to 0 for all t greater than 0. Okay, so what does this mean? So we will go through a few examples to see different kinds of equilibriums that we will encounter. So in the case of a simple pendulum where everything, all the parameters are normalized to 1, I have an equation which looks like this. Okay, so equilibrium points are one where I just say x1 dot is 0, x2 dot is 0, and so on. So what do I get from the first equation is that so this will imply that x2 is 0, which is kind of okay to check that the velocity would be 0 at the equilibrium, and this would mean that sine of x1 is 0, which means it will have a variety of solutions, right. So starting from say pi to 2 pi and so on. So all these multiples of pi. So what is different or unique about this system is that it has multiple equilibria. So if I were just to look at linear systems, we were essentially looking at x dot equal to Ax, and if A was full rank or invertible, then the origin was the equilibrium. So this, to begin with, is a nonlinear system. The nonlinearity appears in this term here, and this system is seen to have multiple equilibria. So if I relate to the phase space that I had drawn earlier for the case of undamped response, so you can see here, right. So this point here is a equilibrium. Sorry. So you can see a couple of equilibriums here, and one at the origin and so on. Okay, sorry, this is behaving weird. Okay, so if I go back to the phase space which I had drawn in one of our earlier lectures, you can see that this actually corresponds to a set of different equilibrium points. Starting from here, you have an equilibrium point here, here, and so on if you keep on progressing to the right and the left. So this is a typical case of a system or a nonlinear systems which has multiple equilibrium points. What are the nature of these equilibrium points? Do each of the equilibrium points exhibit the same behavior or not? That we will see in the due course of this lecture. Okay, so in general, so if we started off with the system ftx, but if the system is autonomous, that which means that the system does not explicitly depend on time, then finding equilibrium corresponds to solving just the nonlinear equation f of x equal to 0. Same in the case of a pendulum, right. So this was an autonomous system, and I was just solving for f of x being equal to 0. Okay, so is it all very obvious in the linear case that the origin is always the equilibrium point? Well, the answer turns out to be not very obvious, but we will look at a couple of examples. So in the linear case, the equation Ax equal to 0. So my dynamics are the form x dot equal to Ax. I set x dot equal to 0. I am essentially solving for this equation. If Ax equal to 0, so this system has a unique solution if and only if, so there is a typo here, A is non-singular or A is invertible. So, in case when A is invertible, I can just write that x is A inverse times 0, that is 0. So, the origin is the unique solution of this equation if and only if the matrix A is invertible. So, on the other hand, if say A is singular, what happens if A is singular? So, let us say I take an example like this, right, x1 comma x2, I am looking for this to be 0. If I just solve for this, what do I get from the phone? That x1 equal to 0, and I do not get any expression for x2, which means that 0 comma x2 is a solution to this. So, what do I mean by this? At any value, right, it could be 0 comma 1 is a solution, 0 comma minus 1, 0 comma 10 and so on are the solutions to this equation. Any value of x2 with x1 equal to 0 is a solution. If I just were to draw it here, x1, x2, so x1 is 0 and x2 being any value. So, this entire horizontal line is a solution to Ax equal to 0 in this case, or it also means that if A is singular, then it has a continuum of solutions, right. So, this is sorry. So, this entire line here is the continuum of solutions for this set of equations or for the system which is represented by A of this form. Okay. So, this is also the null space of A. So, here in the case when A was invertible or non-singular, then the null space is just the trivial point, that is that x equal to 0 is the null space. Well, this phenomena can also occur in the nonlinear case. So, if I have a system which looks like this, x dot is minus a1 plus b x1 x2, x2 dot is so on. So, I just look at the solution of what is the equilibrium, just look at the solutions of f of x equal to 0. The second equation will give me minus b x1 x2 is 0. First equation is minus a x1 plus b x1 x2 is 0. From here I already know that b x1 x2 is 0, therefore, I am left with just this equation, which means that x1 equal to 0. So, this is the only thing that I can derive from this equation, and therefore, 0 and any x2 is a solution to this equation, is an equilibrium point for this system, and therefore, this system also exhibits a continuum of equilibria. An interesting case that throws to us lots of insights into understanding equilibrium points is essentially with second order systems. Well, let us just say I am dealing with second order linear systems, and this linear system could just be linear by itself, or it could come as a process of linearization of a nonlinear systems, that we will do in the next lecture succeeding this lecture. So, let me just make things simple here and say I am just dealing with a second order linear system, which means x dot is Ax, A is R2 cross 2, x is a 2-dimensional vector. Okay. So, for any given some initial state x0, the solution will always take this form, and now we know how to compute e power at. We can also do it via its Jordan form and so on, right. So, e power at, and here j is the real Jordan form of A, P is a non-singular matrix which takes it from a given form to its appropriate Jordan form, right, and P is of course non-singular, and we also know how to derive this matrix P. Okay. So, depending on the nature of eigenvalues, the Jordan form can take several forms. In this case, essentially it will take 3 forms. So, first is when the eigenvalues are real and distinct. So, this will just be the Jordan form will just be a diagonal. So, this should be a lambda 2 here, which means that the eigenvalues are just lambda 1 comma lambda 2. In this case, I will just realize a nice natural diagonal form. In case the eigenvalues are repeated, like lambda and lambda are my eigenvalues, then the Jordan form can take can be something like this, where k can either be 0 or 1 depending on the multiplicity of the geometric multiplicity of the eigenvalues. Third thing is when I have complex eigenvalues, we have alpha plus minus j beta. So, okay, there is an alpha missing here. So, we will have in this case complex eigenvalues. Okay, what do each of these eigenvalues signify? Is there just information on stability, or there is a little more of information than that? And when do these cases actually occur? Okay, so first let us start with the case of real eigenvalues. Okay, what does it mean? Both eigenvalues are real, they are both non-zero. We will come to the case of zero eigenvalues a little later. Okay, so let us say I have this set of eigenvalues. Let me just derive this, and I come back to this slide. So, I have lambda 1 and lambda 2, which are not equal to each other and which are also not equal to 0. And again I am looking at a system with x dot equal to a x. Now, I know in this case that by taking its eigenvectors v 1 and v 2 and a coordinate transformation which looks like this, m inverse x, I can transform this system into a diagonal form, and the diagonal form looks like this. Z1 dot is lambda 1 Z1 and Z2 dot is lambda 2 Z2, and this will have solutions. Z1 of t is Z10 e power lambda 1 t. Similarly, Z2 of t is Z20 e power lambda 2 t. Okay. So, this is just how the solutions would look like. Now, depending on the values of lambda, whether they are greater or less than 0, these solutions will either increase exponentially or will decrease exponentially and tend to the origin. Okay. So, back to here. So, this is what we have now, right. The solutions in the diagonal form are just given by this. Now, I can just eliminate t to write my equations of this form. This is a little straightforward to check also. How do I eliminate t? So, I have these two equations, right. Z1 dot is lambda 1 Z1, Z2 dot is lambda 2 Z2. So, I just have dz2 by dz1 can be written of the form lambda 2 by lambda 1 Z2 over Z1. And I can do all the calculus that I know of solving integral equations, and I just end up with the solutions like this, with C depending on the initial conditions and so on. Okay, so this is like easy to check. Okay, the first case which we would be interested is when lambda 1 is less than lambda 2 is less than lambda 1 and both are negative, right. The first observation is, since both are negative, so I will see it is easy to check that this will go to 0, this term will also goes to 0 as t goes to infinity. Okay, this is kind of obvious. Okay, and if I look at in the Z1 Z2 plane, the trajectories tend to the origin, like so here Z1 also goes to 0 and Z2 also goes to 0. And of course, in this case the 0 turns out to be the equilibrium point. So, the origin is the equilibrium point. Just you can substitute Z1 dot is Z2 dot is 0 and end up with equations lambda 1 Z1 is 0, lambda 2 Z2 is 0, and therefore, Z1 Z2 is 0 comma 0 is the equilibrium point. Okay, so what happens in this case? So, if I look at, okay, so what I know now is that these in the Z1 Z2 plane, the trajectories tend to 0 as time progresses, or exponential or asymptotically. Okay. So, what how do they actually do that? So, from my equation relating Z1 and Z2, I can compute the slope of this line, right. So, how does Z2 change with respect to Z1, right? That is what we that the derivative is essentially the slope of it. So, this is a positive number. Okay. The slope of the curve. So, it is easy to check from here that the slope of the curve approaches 0 as Z1 goes to 0. Okay. Second is the slope approaches infinity as Z1 goes to infinity, right. That is what is happening here, right. So, as the trajectory approaches the origin, it becomes tangent to the Z1 axis. So, if you look at these things, as they approach the origin, they are becoming tangent to the Z1 axis, and away from the origin they will be parallel to the Z2 axis, right, at really at infinity, right. And the second observation is, as it approaches infinity, it becomes parallel to the Z2 axis. You can just plot this for yourself and check. So, we have put up already the code to help you draw phase portraits of this form. We have already done this in our week 1 lectures, a bit of it starting with phase space. So, this is also a continuation to that. There we really did not talk of equilibrium points and the nature of them, but slowly we will get to understand that the kind of things that we are doing today will essentially relate to stable equilibrium points, unstable equilibrium points. If I am talking about stable, I am looking at an under damped situation, I am looking at an over damped situation, critically damped, and so on, right. Okay. So, this is nice here, right. So, I just see that all the trajectories are actually converging to the origin. So, it means that if I am at the origin, I will always be at the origin, right. So, but if I am slightly perturbed here, say so if I say end up at this point here, then I will slowly come back to the origin, right. So, okay, let us go back to the x1 x2 plane and check what is happening here. Okay. In the x1 x2 plane, the trajectories tend to the origin again as t tends to infinity. Okay. Now, we have here eigenvalues which are lambda 2 less than lambda 1, and both are less than 0. So, we call this as, so if this condition is true, then the term e power lambda 2 t converges to the origin faster than e power lambda 1 t. Okay. So, this is faster. Okay. So, we call this the fast eigenvalue, and then the corresponding eigenvector as the fast eigenvector. And similarly, with the slow eigenvalue and the slow eigenvector. So, as time increases, the trajectories become tangent to the slow eigenvector in V1, and as they approach the origin, and parallel to the fast eigenvector away from the origin. So, you can see roughly here that the slow eigenvector should be somewhere around here, and the fast eigenvector like somewhere around here, right. I think you can just quickly check for any example this should hold, right. So, we in the Z1 Z2 plane, it actually looked quite nice of how the trajectories are going to the origin, and here in this case this will be the slow eigenvector, and this will be naturally the fast eigenvector, and correspondingly in the x1 x2 plane. Okay. When such a behavior is seen, the equilibrium point x0 is called a stable node. Okay, because any trajectory starting around the origin will actually come back to the origin. So, we will define the notion of stability formally in next week's lectures, but for the moment we can just observe this and call this a stable node, right. Okay. Unstable node, it's everything is still the same, that your lambda 1 and lambda 2 are right. So, both are positive. So, e power lambda 1 t and e power lambda 2 t will both go to infinity as t goes to infinity. Okay. So, when lambda 1 lambda 2 greater than 0, the exponential terms grow exponentially as time increases. It will happen same. So, if I were to just plot it in the z1 z2 plane, it will just be the same except the arrows being reversed, right. So, all trajectories starting from the origin will, or near the origin, will tend to go away from the origin. Whereas in the stable node case, all trajectories starting around the origin will tend to come back to the origin. If your initial condition is the origin, you will always be at the origin. Okay, so in this case, the equilibrium point is called an unstable node. Okay, for eigenvalues which are greater than 0. Okay, interesting thing happens when we have eigenvalues which are real, but which have opposite signs, say plus 1 and minus 1. Of course, this would correspond to an unstable system. So, we call lambda 2, which is less than 0, the stable eigenvalue, and of course, correspondingly the stable eigenvector, and lambda 1, okay, this should be unstable. Lambda 1 is the unstable eigenvalue and hence the unstable eigenvector. So, lambda 1 is stable and lambda 2 is unstable. This is a little typo here. Okay, so how to understand the behavior of this? Let us again analyze these two terms here. So, I have e power lambda 1 t and e power lambda 2 t. So, lambda 1 is greater than 0, it is the stable eigenvalue, and lambda 2 is less than 0. So, this is the unstable eigenvalue. Sorry, okay, lambda 1 is greater than 0. So, this is my unstable eigenvalue, and of course, the corresponding eigenvector will be called the unstable eigenvector. Lambda 2 is less than 0 and I will call this the stable eigenvalue. Okay, so what would we expect as time progresses? That e power lambda t, lambda 2 t will tend to 0 as t goes to infinity, whereas e power lambda 1 t will go to 0, will tend to infinity as t goes to infinity. Okay, so so let's come back to this. So, e power lambda t corresponds to z1. So, z1 t is z1 naught, z2 t is z2 naught e power lambda 2 t. So, if I were to plot this in my z1 z2 plane, okay, so this plots would look something like this, right. At infinity, well, the z2 will tend to 0 and z1 will go to infinity from starting from any initial condition, this way, and this way. Okay, this is how the plot will look in the z1 z2 plane when we have eigenvalues, one of which real eigenvalues, one of which is unstable and the other one is stable. Okay, so in back to the x1 x2 plane, this would look something like this. So, the stable trajectories are along the stable eigenvector and the unstable trajectories are along the unstable eigenvector. So, this could so you can just differentiate the things here or more naturally over here and so on. Okay. So, in this case the equilibrium point x equal to 0 is called a saddle point. Okay. So, this was about real eigenvalues. What about the case when we have complex eigenvalues? Well, that case also turns out to be interesting. So, when both eigenvalues are complex, I have some eigenvalues, let me call they are alpha plus minus j beta. Okay. So, let us again do this over here. Okay. So, when I have complex eigenvalues, this means my lambda 1, 2, 1 comma 2 are of the form alpha plus minus j beta, and of course, I do the usual change of coordinates from z equal to m inverse x to get my system of the following form: z1 is alpha z1 minus beta z2, z2 is beta z1 plus alpha times z2. So, I just do a little change of coordinates, let us say change to polar coordinates. Okay, what do I have in polar coordinates? R is square root of z1 square plus z2 square, and the angle theta is the tan inverse of z2 over z1. Okay. Now, if I write these equations in polar coordinates, I will have two coupled first order differential equations, that is r dot is alpha times r, and the second equation given by theta dot is beta. Okay. So, for a given initial state r 0 and theta 0, the solutions are of the form r of t is r 0 e power alpha t and theta of t is theta naught plus beta t. Okay. So, this is interesting here, right. So, I see that I have some, if I am looking in the polar coordinates, I am looking at the radius of it, so to speak, which has an exponential term depending on t. Okay. So, if I just say, okay, what happens to the radius when alpha is less than 0? So, I have r of t is r 0 e power, say alpha is minus 1, say e power minus t. So, this will mean that in my z1 z2 plane, my trajectories will just spiral to the origin, say maybe in this way, okay, in the z1 z2 plane, right. It is also obvious from here, right. I start with the initial radius and it will just go spiraling to the origin. Okay. Now, back to here. So, when alpha is less than 0, the trajectory spiral to the origin. In this case of complex eigenvalue, I call my equilibrium point to be a stable focus. Okay. Now, the same thing when alpha is greater than 0. Well, I just see from here that when alpha is greater than 0, r t, which is r 0, let us say alpha is 1, you see that the radius actually starting from some initial radius, the radius actually increases with time, or it, in other words, it just spirals away from the origin. Okay. So, this is z1 z2, so the direction of arrows will be away from the origin. In this case, they will be towards the origin. Okay. In such a case, all the trajectories are going away from the origin. The equilibrium point is called an unstable focus. Okay. Interesting thing happens when r equal to 0. When r equal to 0, in this case, when alpha equal to 0, alpha is 0, r of t is r 0 e power alpha t. When alpha is 0, this is just r. okay, or r0, it just be the radius where it actually started from. For all times t, this will just be for all times t greater than 0. So, essentially I am looking at a circle of constant radius r for all times t greater than 0. Okay. So, if I come back to my x1 x2 plane, so this could also in general be ellipses, right. So, when alpha equal to 0, the trajectory is, so they just are in some periodic orbits around the origin, like here, right, or this one. They are either the circle of radius r in this case, or more generally they will look like an ellipse. So, in this case the equilibrium point is called the center. Okay. So, this also if I look at it correspond to few cases that we learnt earlier, right. So, this is usually the undamped case. Okay. These things would correspond to the underdamped system. Of course, I am not really talking of what is the damping in an unstable system, that really does not make sense. So, these are things that are corresponding to the underdamped case or the underdamped system, whereas I go back here, this would correspond to something like an overdamped system, or when lambda 1 lambda 2 are equal, it will correspond to a critically damped system. And these kind of plots we drew earlier in our week 1's lectures. Now, there we just talked about damping, the damping properties of the system, but this is a little more general way of looking at it. What happens when we have repeated eigenvalues, or for the case when we look at a critically damped system? Well, when we have non-zero repeated values, which means lambda 1 and lambda 2 both are equal to lambda, the trajectories, well, as usual they converge to the origin, and in this case again the equilibrium is called a stable node. Okay, so let's check this in a bit more detail. When we have non-zero multiple eigenvalues, okay. Again I look at okay, so this means essentially that lambda 2 and lambda 1 are equal to lambda, and this is actually not equal to 0. We will come to the case of the 0 eigenvalue a little later. And with the appropriate transformation, I can write the system as z1 dot is lambda z1 plus k z2, z2 dot is lambda z2. So, a couple of cases can occur when k is 0 and when k equal to 1. Okay, when k equal to 0, I am just looking at these two equations, right. Z1 dot is lambda z1, z2 dot is lambda z2. So, if I just compare with the first case which I had of z1 dot is lambda 1 z1, z2 dot is lambda 2 z2, which had the relation between z2 by z2 was given by c times z1 of lambda 2 by lambda 1, okay, and then c was z2 naught by z2 naught by z1 naught lambda 2 by lambda 1. So, if I just compare this to the situation where I will have lambda 1 equal to lambda 2, it should be easy to check the following, right, that if I just draw this in my z1 z2 plane, all the trajectories will be coming to the origin this way, or this way, or this way. Okay, so this is like a little contrast with the slow and fast eigenvalues and eigenvectors and so on. Okay, so what is also interesting is the case when k equal to 1. Okay, this should be easy to plot and you can just check by yourself. So when k is equal to 1, then I have z1 dot is lambda times z1 plus z2, and z2 dot is lambda times z2. So the solutions would be z1 of t is e power lambda t, z1 0 plus k z2 0 t, z2 of t is e power lambda t z2 of 0. Of course, if I just want to write it in terms of z1 and z2, that will simply be z1 is z2 of z1 0 by z2 0 plus k over lambda log of 2 by z2 0. Okay. So, I will just not plot this, but we will just check what this means in the x1 x2 case. So, it will turn out not surprisingly that you are actually talking of a stable system because the eigenvalues are less than 0. We are talking of eigenvalues being equal to each other. So, we are talking of some critically damped situation where we would naturally expect the trajectories to come back to the origin starting from a neighborhood of the origin. So, this is how they will look like, and we will also call this as a stable node. What happens when it is an unstable node? Well, just the plots will be similar with just the eigenvalues, with just the direction of the arrows being reversed. So, naturally I am looking at say eigenvalue of +1, the system will naturally be unstable, and this equilibrium I will call as an unstable node. Okay, the next thing that we will discuss is an interesting case when there is a possibility of having a 0 eigenvalue. Okay, so let us start with just one of the eigenvalue being 0. Let us say lambda 1 is 0 and then lambda 2 is less than 0. Okay. So, how will how will the system look at how will the transform system look like? So, when I just write it in this Jordan form. So, lambda 1 is 0, lambda 2 is not equal to 0, and I just again use a transformation matrix V1, V2, and via the transformation Z is m inverse x. In my new coordinates I have z1 dot is 0, z2 dot is lambda 2 z2. The solutions are pretty straightforward to compute. Z1 of t will just be whatever it began with its initial condition. Z2 of t will be z2 naught e power lambda 2 t. So, if I were just to plot z1 and z2, say for initial condition over here, z1 would just be here, and if lambda 2 is less than 0, the trajectories would just behave this way. Say if this is the initial condition of z1, then the trajectories will be here. If this is the initial conditions, the trajectories will go this way for all lambda 2 which is less than 0. Okay, so what does that mean, right? So, first is the matrix A has a non-trivial null space, and any vector in the null space of A is an equilibrium point of the system. Okay, how will we deduce the equilibrium point? So, if I have a system like this, z1 dot, z2 dot is 0, 0, 0, lambda 2, z1, z2. What are the equilibrium points? If I just solve for this, I will have lambda 2 z2 equal to 0, which means z2 equal to 0. Okay. Then this is the only solution I get from solving this. So, any point of the form z1 comma 0 is an equilibrium. is an equilibrium point of the system, or in general here I will have an equilibrium space instead of an equilibrium point, right. So, any point, take any z1 with z2 equal to 0. So, 1 comma 0 is an equilibrium, similarly is 10 comma 0, minus 10 comma 0 and so on. Okay. Now, when lambda is less, lambda 2 is less than 0, all trajectories converge to the equilibrium space. So, what is the equilibrium space here is this entire z1 axis, right. So, any point in z1 with z2 being equal to 0 is the equilibrium space, say here, or let me just draw it in the red. So, this is my equilibrium space which is obtained by just this one, this is my equilibrium space. So, when lambda 2 is less than 0, any trajectory, right. So, let this trajectory, each of this trajectory will converge to the equilibrium space. Okay. Next, what if lambda 2 is greater than 0, everything will be the same, the matrix A will still have a non-trivial null space, and any vector of in the null space of A is again the equilibrium point, and the only thing that will change is all the trajectories diverge from the equilibrium space. So, let me just draw it here. Okay. So, the trajectories, so this is z1, this is z2, and this will just be my trajectory. So, all trajectories will go away from the equilibrium space. The equilibrium space is the entire horizontal axis in this case. The last case that we will look at is the case when both the eigenvalues are 0. Okay, not surprising to note that the A matrix will still have a non-linear, the A matrix will still have a non-trivial null space. So, in this case when both eigenvalues are 0, we can potentially look at two cases. So, I am looking at both eigenvalues lambda 1 and lambda 2 being equal to 0. So, one case could be that I am looking at systems of the form x1 dot is 0, x2 dot is 0, or in other words x dot is the 0 matrix times x. Okay. So, this will have both eigenvalues to be 0. This would correspond to the case when the null space is of dimension 2, and not only that, every point in the plane will correspond to an equilibrium point. Okay. So, this case is okay. It may not be too interesting for us to look at the phase plane, but what is interesting is the case when both eigenvalues are 0 and the dimension of the null space is 1. Okay. In how does that happen? That could happen in cases when well, I have systems of the form z1 dot is z2 and z2 dot is 0. So, in this case the A matrix is of form 0 1 0 0, and if you compute the eigenvalues they will turn out to be 0 comma 0. So, the A matrix is not completely 0 here, it has a non-zero entry here, but still both of the eigenvalues are 0. You can compute check this as a simple exercise. Okay. Okay, so it may not necessarily be in this form all the time, but via some appropriate transformations you can write the systems to be in its form. So when does this case happen and when does this case happen? It again is the same, that you are looking at a certain Jordan form. So if you compute the Jordan form of this form, you can check its algebraic and geometric multiplicity and check its algebraic and geometric multiplicity, and you will have the appropriate Jordan form. So this is the Jordan form when the algebraic multiplicity is 2 and the geometric multiplicity is 1, whereas here it will be a slightly different case. I'll leave that as an exercise. Okay. So this case is a little interesting to draw the phase space. So what can I see directly even without worrying about the solutions is that Z2 is a constant and Z1 dot varies positively with Z2 or with the sign of Z2. If it is minus Z2, then it will vary negatively with increasing Z2 and so on. Okay. So how does the solution look like? So I will have Z1 of t is some initial condition Z1 0 plus Z2 0 of t, and Z2 of t is Z2 0. Okay. Now, what is the equilibrium space? So, in this case, well, you can check easily, right. So, I am just looking at the solutions to this one for Z1 and Z2. So, this will give me that Z2 equal to 0, and therefore, the entire Z1 axis is the equilibrium subspace. Actually, it is called this equilibrium subspace. So, if I were to plot on the Z1 Z2 plane, so this entire Z1 axis is my equilibrium subspace, the Z1 Z2 plane. Okay, what happens close to the equilibrium? It's easy to check that my phase curves will just be parallel to the equilibrium space or the equilibrium subspace. So, here they will just be the reverse sign. Okay. Now, so there could be another cases when Z1 dot is negative of Z2, Z2 dot is 0. What will happen to the phase curves? They will be exactly the same, just with the directions of arrows here and here being reversed. Okay. So, that is like two different cases when lambda 1 and lambda 2 both are equal to 0, and the equilibrium subspace depends again on the Jordan form, right. So, when the algebraic multiplicity is equal to the geometric multiplicity, the Jordan form simply has this form, and the equilibrium subspace will have dimension 2. Whereas, in this case the Jordan form takes a form like this, and you will have solutions or the phase space given by this set of equations. So, to summarize, when both lambda 1 lambda 2 are equal to 0, case 1 the dimension of the null space is 2, again depending on the Jordan form, and the case 2 the dimension of null space is 1. And if I were to plot in general in an x1 x2 plane, all so the equilibrium subspace could be somewhere like here passing through the origin. So, all trajectories starting off the equilibrium subspace either here or here, they will just move parallel to it, similarly to what we saw in the plots in the Z1 Z2 plane, and equivalently in the x1 x2 plane they will look something like this, right. Okay. So, just to conclude, we have defined the notion of an equilibrium point. We did a lot of analysis, qualitative analysis for several equilibrium points of second order systems. We had real eigenvalues, complex eigenvalues, repeated eigenvalues. What if one or both of the eigenvalues go to 0? That contains a bit of a rich information of what will be useful for us in stability analysis. So, just to conclude this week's topics, we will deal with limit cycles, which is a very interesting property of linear systems, of nonlinear systems, which not necessarily exists in linear systems. And then we will look at couple of or few methods of linearization of how do we start from a nonlinear system and end up with a linear system. So, that will be in the next lectures. Thank you.